Well, hello. Today's little video lecture is designed to give you some basic background on properties of waves and wave characteristics, types of waves, some of the things that we use to describe how waves move, and things along those lines. We have a couple of cat guests today. Apparently they're fascinated with why I'm talking to my computer. We have Bubba, who's really bored, and we've got Fozzie over there, who knows what he's up to. But anyway, hopefully they will not do much. Anyway, so today we've got properties of waves. On this first picture here, you can see a couple of different images of some waves. There's a electromagnetic field wave up in the top left. My favorite, coffee, of course, on the right. And you can see the ripples, of course, is where the wave is. The slinky dog. How can you not love a slinky dog? I wish I could get an animation of him in motion, but anyway, he's a great example of waves. And then the bottom, kind of a cool, or just a graphic of what waves look like. So let's take a look at how waves form and what they're all about. So first things first, mechanical waves. I'll talk about electromagnetic waves in a second, but mechanical waves, every single one of them has to start with some sort of a disturbance. Something has to get matter moving around a little bit, and it could be touching something, it could be a drop, it could be a shove, but whatever, some sort of a disturbance has to kind of transmit some energy to the matter that's around it. Then once that energy has been transmitted, things kind of start vibrating a little bit. That energy has to travel through a medium, and a medium by definition is the physical matter through which a wave is traveling. All mechanical waves require a medium, electromagnetic waves do not. We'll get there in a minute. So a medium could be anything like water, it could be air, and it can be earth, it could be a slinky, anything that that wave is traveling through. And then finally, all waves are responsible or involved with transferring energy through particles basically across distance, across space, or not space like a vacuum, but across, from left to right. So those are the three things that we need to have basically a mechanical wave: some sort of a disturbance, some sort of a medium, and then some sort of energy transfer between the different parts. So like I said, not everything requires a medium. Electromagnetic waves are very different kind of wave than what we're talking about in this unit. They can travel through medium as well, but they can also travel across vacuum, across space. So things like visible light, infrared, gamma rays, those sorts of things travel across space. But magnetism also can travel through space as well, and electrical energy can, believe it or not, travel through space. Not electricity, but electrical energy. It's a little bit different. We're going to talk about those in depth later on this semester, so we don't need to worry about them right now. This particular part, we're talking about mechanical waves, like sound waves. Don't think of sound as being a wave, do you? But seismic waves or earthquake waves. My favorite, the slinky that the guy's playing with over there. Water waves are a really obvious example. All of those require some sort of a medium to travel through. So in terms of how they travel, we have to a little bit differentiate between the two kinds of waves, and then the difference between a wave pulse, which is the single bump that you would make, and then the wave itself, which is actually the direction of energy transfer. So the wave pulse is when you make a big lump in a slinky, for example, or you throw a rock into a pond. That's that initial wave pulse. That is going to determine how energy travels through the medium. But the medium itself moves in response to the energy in a way that's different from how the wave travels. And this gets really odd. So let's take a look at our two different kinds of waves. We've got two kinds here. We've got the longitudinal wave, and then we've got the transverse wave. And you've made both of these in lab now with slinkies. The longitudinal wave is a push wave. It's also known as a compression wave. And the transverse wave is a typical side-to-side or up-and-down kind of wave like you see in water. With a longitudinal wave, think about what you're doing. You're shoving something end to end. And when you do that, the wave is going to travel from, in my perspective, right to left. Or in the picture here, it shows it from left to right. And you can see the energy transport down at the bottom down there. The individual particles of the slinky, however, move like this. The wave goes like that, but the slinky goes like that. Thanks, Bubba. I guess he was really bored. He had to leave. In a transverse wave, you have a little bit different. You go like this with the wave. The wave still travels down the length of the slinky, but the parts of the coil actually go this direction. So in both cases, in the diagram that you've got in front of you, in both cases, the wave motion is going from left to right. This one shows it going from left to right as well. But in a longitudinal wave, the compression wave, the particles of the matter actually kind of go left to right, sort of in the same direction as the wave travel, but sometimes opposite their direction. In a transverse wave or a water wave, you can think about it that the water is actually moving up and down, but the wave is going left to right. or in the picture on that you've got right to left. Think of it like a wave traveling across a lake and a duck floating on the lake. If you watch the single wave, it could be moving across the wave, right? But the duck is just going to go bob up and down. So that's the difference between movement of the medium and movement of the wave pulse itself. So let's talk about how to characterize the different sizes and shapes of waves that we have. So first of all, typically we talk about waves in sort of a sine wave kind of pattern. A sine wave is due to not just one wave pulse, but repeated wave pulses. And if those wave pulses happen at regular time intervals, that's simple harmonic motion. So basically a sine wave is a type of wave that's the result of matter vibrating in simple harmonic motion. First and the most important thing that we typically do, not most important I guess, but first kind of most obvious thing that we use to characterize waves is something called wavelength, and that's exactly what you think. It's how long is the wave itself, how much is the space between the different crests. This funky letter right here, this thing, is the Greek letter lambda, L-A-M-B-D-A, lambda, and it's kind of got a wavy shape to it itself, so it kind of may help you remember which one it is. But anyway, that's the symbol that we use to represent wavelength. We do not use a W. I don't know why. But the wavelength is simply the distance between crests. So you could say the distance from here to here maybe, or you could say the distance between troughs. That would work, from there to there. Or finally, you could say the distance of a complete cycle. So from middle to up to down and back to middle again. This last picture kind of shows that this is one complete cycle. So that could also be counted as a wavelength. Basically whatever's easier for you, depending on the medium that you're measuring. Second thing we can talk about is amplitude. Amplitude is the size of the crest. So you can think about it when you're swimming out in the ocean. The waves are, there's a certain distance between the waves, but probably more important to you is the size of the wave. Is it just a little ripple that's going to splash your ankles, or is it, a big tsunami that's going to come and wash you up on shore? And amplitude is related to the size from the midline to either the top of the crest or the bottom of the trough. And the important thing about amplitude is related to energy transfer. The bigger the energy transfer, the bigger the amplitude. Not necessarily the wavelength. The wavelength is the distance between the wave pulses, not how big the pulses are. So a little bit of a different idea. Let's move forward. We can talk about this also with longitudinal waves. Longitudinal waves are compression waves. And again, sound waves are a really good example of this. Wind is another example that can actually be a longitudinal wave. But a longitudinal wave has two different things. It's got compressions like this, areas where particles are closer together. And again, think of our slinky where the coils are real close. And then it alternates with areas that are lower pressure, or areas where the particles are further apart, or like the slinky coils are further apart. Well, we can plot this, just like you see up here, kind of like a sine wave. We can turn a longitudinal wave into something that looks like a transverse wave. So we can still talk about things like amplitude. We can still talk about things like wavelength as well. And again, wavelength is simply the length between crests, which in a transverse wave, or a longitudinal wave like this, would be the distance between maximum compression to maximum compression, something like that. So again, it's just a slightly different way of looking at it. I didn't want you to be confused if you're thinking about sound waves or something like that. How can that possibly have a wavelength to it? Next concept is something called frequency. Frequency is abbreviated by this kind of cursive letter F. You may also hear me use the letter nu, which is a Greek letter nu. It actually looks kind of like a V, which is why they don't use it in your textbook, because the V for velocity looks a lot like the nu for frequency. But if you hear me say nu, the knights who say nu, it is a different way of doing frequency. Sorry, it's kind of old school, my bad. But a frequency is a measure of how often a wave crest passes a certain point. It's not a measure of speed. We've got to be a little bit careful. Sometimes we say that a high frequency wave is faster and a low frequency wave is slower. We've got to be a little bit careful with that, because faster and slower should be reserved for speed, but we'll get to that on the next slide. So again, frequency is how many wave crests pass a point in a certain given amount of time. So if you think about our diagram down here, we have kind of like a start line and we have kind of a finish line. And if we can kind of did like that was a 1 second of time, then this top wave would only have, there's 1, 2 wavelengths. It's pretty low frequency. It doesn't have a lot of wave crests passing by that space in a certain amount of time. This bottom one, obviously quite a bit faster. There's all kinds of wave crests passing by. I don't know, 1, 2, 3, 4, 5, 6, 7 can pass through in that same amount of time. That's a much higher frequency wave. And as you can see by the bottom, it kind of makes sense that frequency and wavelength are inversely related. The longer the wavelength, the fewer wave crests can pass in a certain amount of time. So higher wavelength means lower frequency, and lower wavelength equals higher frequency. for a given kind of a wave. So that kind of makes sense. You can see it, especially on this picture here. Last thing about this I want to mention is that the units of frequency are very strange. The units of frequency is a count per second. So you could say it's 2 per second or it's 8 per second. So it's actually kind of a weird unit. It's not 2 seconds, it's 2 per second. We also call that unit a hertz, H-E-R-T-Z. You've probably heard of hertz before. It's a lot of times used to characterize sound pitch, for example, megahertz, your radio stations, things like that. But that's a per second. It's a weird unit. You'll kind of get used to using it. Okay, moving along. Last bit, wave speed as opposed to wave frequency. Wave speed is a measure of how long it takes a wave pulse to cross a given distance, to cross space, for example. The speed of light, for example, 300 million meters per second. In other words, if I were to shine a flashlight, 1 second later, that wave pulse would be 300 million meters away from us. It's ridiculous in 1 single second. Sound's quite a bit slower. You can see actually I've got the speed down at the bottom here. Sound, if I go boom, it's actually only going to go 343 meters in a second, as opposed to light, 300 million meters in a second. So again, velocity is how fast it crosses space or distance, and velocity, just like anything else, is distance divided by time. Same thing is true here when we're talking about waves. Here's our formula. That doesn't look like distance divided by time, Mrs. Bedwell. It is, I promise, because wavelength is a measure of distance, and frequency is a measure of per time. Remember, seconds was on the bottom, not on the top of that. So frequency is actually per time. So it's distance per unit of time. Again, it looks kind of weird to us, but velocity is frequency times wavelength, or lambda nu, as you'll hear me say in class. So I apologize, old school. In any case, one of the things to keep in mind, wave speed is actually a constant. For a particular kind of a wave in a particular medium, particular temperature, it's something that it's not affected by the wavelength, it's not affected by the frequency, because they're inversely proportional. It's not affected by amplitude. So if you think about it, if you've got a long slinky and you make a big wave pulse and you watch that pulse go to the other end, it doesn't matter what you do to that wave pulse, to that slinky, you can't make that wave go any faster. Go ahead, I dare you to give it a try. But it's going to travel from one side to the other end of that slinky in a certain amount of time, no matter what you do to it. You can't just wiggle it faster, you can't wiggle it bigger. That's its velocity. Now, velocity for a particular type of wave is a constant. For light, again, 300 million meters per second. For sound, about 343 meters per second, depending on the temperature of the air. By the way, this picture on the left, and this is the last thing we'll do, I just wanted to kind of show you this kind of odd thing. This is what it looks like, or this is what happens when a fighter plane exceeds the speed of sound. In fact, it crosses the sound barrier is what they would call it. It's a sonic boom. The fact that it's moving faster than its own sound, faster than 343 meters per second, creates enough energy, enough vibration in the air that it causes the water particles in the air to condense, and it actually forms a cloud right at the back of the plane. It's not that the plane's flying through that cloud, that's where that cloud is forming in that one particular spot. Anyway, thought you might find that interesting. So this little lecture here has been about properties of waves, longitudinal waves versus transverse waves, what a medium is and what the idea of a disturbance is, direction of wave pulse versus the direction of movement of the matter itself, the medium itself, and things like velocity, amplitude, frequency, and wavelength. Hope you enjoyed it.